Okay, I'm gonna go ahead and get started. I know I want to definitely have a few minutes at the end for questions. I'm sure there's going to be a lot of questions, but hello and welcome everybody to the FLATE webinar series. Today's webinar is on data analytics and manufacturing, data collection to decision making. Just want to recognize the FLATE team. We're small and cover the entire state. They're a really dedicated group of people helping to increase the awareness of manufacturing, get more parents, teachers, and students into manufacturing or aware of manufacturing. My name is Ernie Friend, the executive director. We also have Dr. Marilyn Barger, Daniele Orzo Cole, and Teresa Potter on the team. So they're all in this call. So thank you, team, for doing a great job for this webinar. The vision of FLATE is to drive Florida's world-class manufacturing workforce education and training. And that's what we work on every day, trying to create new programs and get more people interested in manufacturing careers. Some of the things that we do is curriculum reform and development. Like as I mentioned, we work with schools all across the state to create new programs, student pipeline development, helping schools understand some of the different ways that they can attract students, and professional development for educators. This is an example of that, this webinar. And there's a whole series of those, which we'll post some links on that later on. So as far as the student pipeline development goes, we do that by helping promote manufacturing education. We do support manufacturing day or month student events. We've got a really cool manufacturing dashboard that gives you lots of information about careers in manufacturing. We host the Manufacturing Educator Awards program. We publish a monthly newsletter. We also provide support for STEM summer camps and develop and disseminate resources for recruiting girls in STEM and manufacturing. Okay, for on the professional development for educators side, we host something twice a year called the Forum for Engineering Technology Education, or as we call it, the ET Forum. We do technology demonstration projects, educator workshops, in person and online. Also provide conference attendance support for faculty. We do online webinars, which this is an example of. And we also do some program mentoring or help schools when as needed when they have issues with their programs or maybe want to improve or start programs. Okay, a couple of links that we have. Excuse me. One is the deflate.org. And from there you can get to these other ones, but flate.org has a host of information. You can find a link to the dashboard, outreach materials, the webinars, that kind of thing. The Made in Florida .org website is a really good website. That and the wiki have lots of great information about Manufacturing Month, or maybe some resources to do some activities in the classroom. So those are, three great resources. And in addition to that, as I mentioned, the dashboard, if you go to flate.org, you can kind of see right there, there's a link to the dashboard from there. Okay, it is my pleasure to introduce this fantastic group of researchers, and they're going to present today on data analytics and manufacturing, data collection to decision making. So with us today, we have Dr. Deep, Dr. Lee, and Dr. Kim. So Dr. Kim, let me hand it over to you.
Thank you, Ernie, for nice introduction. Hello, everyone. I'm Minhee Kim. I'm an assistant professor at University of Florida. Today, I'm joined by my colleague, Dr. Akash Deep from Oklahoma State University and Dr. Lee from Texas A&M University. Today, we're really delighted to talk about data analytics in motor manufacturing systems, where we cover from data collection all the way up to decision making. So this is the brief agenda of today's webinar. I will first talk about the importance of data analytics in manufacturing and talk a little bit about how we can collect data in motor manufacturing systems. Then my colleagues will talk about how to use this data to do quality control and decision making. And lastly, we will provide concluding remarks and discuss some collaboration opportunities. So AI, artificial intelligence, most of everyone are familiar with the importance of AI and how it rapidly transformed the industry landscape. But maybe AI is not the first application that comes to our mind when we think about AI. But the thing is, if you see the right-hand side pie chart, if we combine two main manufacturing applications, discrete and process manufacturing collectively, you can see that surprisingly, collectively, they account for more than 50% of AI spending in 2023. So you can see that manufacturing is actually a really key application of AI spending. And AI in manufacturing is not only just automations, it goes beyond automations. It's about optimizing the production efficiency. It enables things that were not possible beforehand, like predictive maintenance and real-time quality control. And most importantly, it allows us to derive useful insights and make smart decisions backed by the data, backed by the information. So what is AI? What is artificial intelligence? We all heard about it many times in different sources. What's the formal definition of AI? In fact, there are many formal definitions defined by many organizations, universities, research groups, governments, and so on. Here, I just brought one example, which is the definition by EU. And there are different jargons in these definitions, but one thing I like to point out is its emphasis on the data. It says it's about data acquisitions, collecting the data, and how to interpret this collected data, reason on the knowledge, and process these informations. And extract use these informations to make the best decisions, best actions to achieve the goal. So the AI, you can see that AI is definitely founded on the data we collect. So there are three main steps in terms of data-driven decision making. We have to acquire the data, we have to process this data and make the decisions. So you can see without reliable data collections, we cannot proceed to further data analytics or data-driven decision making. So collecting high quality, multiple heterogeneous data sources, that's like the foundation of AI enabler. So what kinds of data we can collect in manufacturing, and we are collecting in modern manufacturing systems? There are different types of data. First is machine data, such as machine speed, or we also collect process data, such as throughput, product efficiency, and so on. We collect data about the environments, like external environments like humidity, temperature that the machine is operating, and so on. We also collect data about maintenance, such as what kind of maintenance we performed last time, when did it performed, who performed this maintenance, and also we can collect data about supply chain systems. And what enables us to collect these types of what enables us to collect different types of data that I just showed you? One key enabler is the accessibility of the sensors. So you can see in this chart that the price of the sensor continuously declined until these days. So for instance, let's say 5-10 years ago, although we know that the temperature this machine is operating is very important in terms of product quality. We know it's important, and we know that there is a sensor out in the market that allows us to collect this temperature data. We did not use it because it was very expensive. We cannot just buy and install it in every machines. But now sensors got much cheaper and it becomes much easier to use. What we do is instead of dispatching human operators to manually collect this temperature data maybe twice or 3 times a day, we're now able to install these sensors to continuously monitor the temperature data. So that's what's possible in modern manufacturing systems. Then, okay, we are continuously collecting data from multiple sources. Then how can we combine the information collected from different resources in a seamless way? The answer to this question is IoT, Internet of Things. So literally it's about internet, just like the internet we use to send out emails, do Google search. But we're talking about Google Internet of Things, Internet of the objects, physical devices. So in manufacturing, this can be different machines. So instead of this different machines operating in silos, now we have this network of different machines. So machine is not only just operate in silo, but it can collect data and share the data with different machines. So now we have this network of physical devices. So why this IoT is very important. So one of the most exciting aspects of IoT is that it bridges this gap between IT, information technology, and OT, operational technologies. So traditionally, IT is about data collection, transmission, communication. On the other hand, OT is about physical device process management on the factory level. And what IoT does is that it combines these two together to unlock this potential. And it is predicted, it's a prediction from Cisco. It says that IoT market potential will be able to reach $14 trillion. And with savings coming from different aspects such as asset management, employee productivity, customer experience, and so on. And again, this IoT, this $14 trillion is starting from these advanced sensors, which will allow us to collect the data. So these sensors will be our eyes and ears to continuously collect the data about machines, about environments, about operators, to allow us to proceed to the next steps, to allow us to proceed to the next step of data analytics and data-driven decision-making. And of course, there are multiple challenges we need to overcome to unlock this full potential. In terms of technical challenges, we may collect too large volume of the data, or the data is not enough, or we have challenges in terms of data variety, data latency, quality, and security. So these are all technical challenges. Of course, on the other hand, there are non-technical challenges. For instance, now we have to address new regulations about data protections and privacy, or we may suffer from lack of analytical talents, to collect and manage this data. So it is very important to address this data to unlock the full potential of IoT and AI in manufacturing. So lastly, I also like to briefly talk about data transmission. So once we collect data using these sensors, what do we have to do? We have to transmit this data to the central server so that we can process this data, right? And in terms of data transmission, there are two types of data transmissions, which is wired networks and wireless networks. So in short, wired networks, it is limited due to these physical constraints and it requires high initial cost. But on the bright side, oftentimes it is faster than the wireless networks and it is more secure. And on the other hand, wireless networks, it is more flexible, but it can be slower than the wired network and more prone to the cybersecurity attacks, which arise as one of the most important challenge in modern manufacturing. So to decide which option is the best, we have to consider different characteristics. So far, I introduced you how we can collect data in the production line using different multiple IoT advanced sensors, how we can transmit this data to the central server like data cloud. So next, our colleagues will explain how to analyze this data to derive useful insights and make decisions.
Thank you, Minhee. So my name is Jaesung. I'm an assistant professor from the Texas A&M in Industrial and Systems Engineering. So my research interest lies on the smart manufacturing. So we've been working on a lot of research to make the existing manufacturing system into the smart manufacturing system. This is an example, like the figure of the smart manufacturing systems. So you can see, so from the manufacturing manufacturing lines. So there are a lot of sensors are attached, and then during the manufacturing operation, we observe these sensor data. The collected sensor data are stored into the cloud, or the data storage, and then those stored data is sent to the data analytics center. So we establish a lot of methodologies for the data analytics to achieve the higher throughput or higher production rate, or to reduce the cost. And also we can do the real-time process control. And then, so finally, we will make the manufacturing system smarter and better. So I will talk about monitoring and detection by the AI, or the machine learning methodologies, and diagnosis and modeling and prediction for the specific application, AM, the additive manufacturing. Or also, I will also introduce the data-driven design and control methodologies. All of those will be explained at a higher level. So don't be nervous with all the technical detail. So I will just go with just an example. So I want to start with the example, the story. So I've been working with a company called the Crider Food. It's a canning company. They make all the different types of canned food, including the chicken can. But one of the biggest issue in their line is oftentimes there was some failure in the system. So for example, if the input can is dented, then during the simming process, while you're adding the cap of the can, so it won't feed, of course. But then so while it goes through the line, all the contents just overflow, and it makes all the system messy. It's not about the mess. So we need to stop the machine, and the operator, the maintenance crew comes in, and then they need to clean everything, and then they need to check all the details of the machine. It costs a lot of it incurs a lot of cost, and it also involves safety issues and sanity issues. And they make the hundreds of cans per second. So you can imagine how much the cost this small incidents will incur. And this is not only the one single instance. They have multiple types of failure. And then every time that happens, they will incur a lot of cost in it. So they wanted to make the system into a smart manufacturing system. So first thing that we did is installing the sensors. So we installed a lot of different types of sensors, including the cameras, video, to collect the videos. And we also attached some vibration sensors and temperature sensor and sounds. And so with all these sensors, we could feel, the AI system can feel and see what's happening in the system. And based on those sensor data, we identified when the failure happens. And also, with a predictive model, we could identify when the failure happened in advance. So even 3 seconds in advance will make everything different, because you can stop the process, and then the staff can come in and fix it. So with all these smart manufacturing system, they could save a lot of cost, and also achieve the safety in the manufacturing system. Traditionally, when the manufacturers are doing the quality control, usually it means the statistical process control. In a simpler term, it's a control chart. It's called the short chart, this is a simple example. So what I mean by the control chart is we collect some data. It may be product dimension, quality, or the throughput, or the production rate, or any variable that you are interested in. And then you mark those data points over time onto the chart. Based on those historical data, we can obtain some probability distribution of those data points. Then we can obtain the upper limit and lower limit that indicates the system's condition. If the data points are located within those control limits, we regard the system as a normal condition. But once those data points go above the upper control limit or below the lower control limit, we regard them as some alarm, because the probability of those going above or below the control limit is very low. So for this, we can also consider the external factors like the temperature or any environmental factors. Next page. However, the limitation of those control chart is the data. As Dr. Kim mentioned, we obtain heterogeneous types of data. We oftentimes collect the sound data, vibration data, image data, or video data, name it. There are a lot of different types of data available, and we want to leverage those data. So by using the AI system or the machine learning methodologies, we can take those input data and get the alarm from the system when the system is going through some abnormal conditions. Well, we can do a lot of things. And some of those will be shown in the following slides. So sometimes manufacturers are interested in not only to know when the failure happens, but what to do next. So let's say the control chart or the AI-enabled the alarm system shows that there is something wrong in your system. Then you want to fix it. But then what to fix is a follow-up question. It's an important question. However, the measurements is sometimes not indicating the operation itself. So in that case, we need to do some analysis. So that can be done by the machine learning, the modern machine learning methodologies or the statistical approaches. So, and this kind of technique is called the root cause analysis or diagnosis problem. So basically, given the limited number of sensors, we want to identify where the problem happens so that we can fix it. So another application of AI is the prediction or simulation. In the past, people use physics law and made some numerical simulation systems to make the digital twin of manufacturing processes. However, it takes a couple of hours or even a day or two. So for example, this is a metal-based additive manufacturing process. So there you have a powder bed, then the laser melts down the powder, the metal powder. Once the powder goes from the left to the right, then it will melt down the powders, and then it will create some line. So you can imagine commercial like the 3D printer you can see everywhere. But this version is for the metal parts, metal products. So instead of just using the physics law to simulate it, we can incorporate this physics law into the machine learning system, machine learning methodologies. And here in this animation, is a blue cube. You could see some red dots, red circles are going left to the right. And it was simulating the temperature change of the metal powder. Why do we simulate the temperature? Because the temperature is the key source of this manufacturing process. Temperature determines everything about the parts, manufactured part. So what I want to show in this slide is we can use the data, but we can also incorporate some domain knowledge into the machine learning methodologies. So assume that you have all the data or the simulation. Then sometimes you want to optimize your process parameters. You want to optimize your manufacturing system. Then how? So this is where the robust parameter design comes in. So this is a figure about the stochastic system. By stochastic system, given the process parameters or control variable or the system parameter, given those, you will have outcome shown as a y. However, it's always not like the fixed relationship. Sometimes because of temperature changes, humidity changes, because of those unknown variations, the output is not always fixed. So oftentimes, can you click it once more? So oftentimes, you want to maximize overall performance while you want to minimize the variation of the performance. So that's the goal of the robust parameter design. Sometimes you just want to maximize the overall performance. That's okay. That is determined by the manufacturer or someone who has has to make the decision. And by the stochastic system is too vague. So by the stochastic system, what I meant was for example, additive manufacturing processes or sensor design or the product design or anything. So you can imagine the different types of processes and systems. One of the way to achieve the optimal process parameters or the system parameters is by using the design of experiments. It's a conventional classical approach by using the statistical theories. So basically, you divide the value of the variable. For example, let's say the x1 is the speed of the operation, and x2 is the size of the tool. Then you divide it into 5 values of both of those. Then you will have 25 points. So at each of the 25 points, you do the experiments with a different speed, with a different tool size. With all of those collected data, and you make a the predictive model and select the process parameter value that achieve the best performance. So this is called the design of experiments. Can you go to the next slide? So nowadays we have all the AI systems. It can enable the efficient process optimization. So it's called iterative optimization. So by using the predictive model, we predict the cost or the quality or the something that you are interested in, key characteristic information. Then we can also quantify the uncertainty related to that prediction. For example, for most of the points, most of the process parameter values, we haven't done any experiments, so we don't have any clue about how much of the cost it will incur or how good the quality will be. Then the uncertainty will be higher. So by considering both the predictive prediction and the quantified uncertainty, the AI system can suggest what parameter set you need to do the experiments to achieve the best parameter, to find the best parameter with a minimum number of physical experiments. So this is done especially when the physical experiments are very expensive. Can you go to the next page? Thank you. This is my last slide. So we oftentimes make the decision not only one time, but we want to find the optimal process parameter during the operation. For example, let's say you are driving a vehicle. So overall, many times you can just go straight, but oftentimes you need to make a left or right. Like during the operation, the temperature sometimes goes up and humidity will change, or many environment parameter will change. Not only the environment parameters, but also in the process parameter, some parameters in the system. Then, depending on those information that we have, we want to optimize the process parameter real time. So this can be done by the automated control and with the AI and machine learning systems. So basically, we predict, there is a predictive model that predict the future, the events. And then based on all these predictive model information about the future, we optimize the process parameters real time. So by doing so, we can make your manufacturing processing system smarter and better, more efficient and effective. And yeah, this is the end of my slides. And I will pass the floor to the Dr. Deep.
Okay, thank you so much, everyone. Thanks to FLATE again for this opportunity. My name is Akash. I'm also an assistant professor at Oklahoma State University. So, what we have talked so far is about, how do we enable this transformation from, traditional systems to smart systems. And Dr. Lee recently, just discussed about different processes and different opportunities within these manufacturing processes where we can use these data-driven insights to improve. What I will be talking about is more, on the asset level. Now that you have machines, you have equipment, you have forklifts, you have different type of things. And so it's not just about the manufacturing process, but also about the production equipment, which you want to keep healthy. You want to, stay ahead of them. You don't want unwanted downtime and so on. So if you go to the next slide. What I probably want to show you is, let's say, if you look at this picture, assume just forklifts, but you can substitute it for any production system. And you have a lot of sensors now. Instead of just being a traditional forklift, it tells you what's going on with it as, any operator is using it. And as one can imagine, from a point of view of reliability, maintenance, or health of this machine, over time, there are going to be many events that might be happening. So let's say, there can be some warnings, probably like, motor temperature increasing, or maybe there is some calibration error and so on. Perhaps there can be some failures too, which can lead us to, kind of do some corrective maintenance on this equipment. And maybe there are some just logs you have that when the machine is being used or so on, right? So what our goal here is that, we want to predict, we don't want our, these critical equipment to fail randomly because that's not good. And so we want to be ahead again in terms of that. But as you can imagine, right, these are, most of the time, these are complex production or manufacturing equipment, and it's pretty similar to, like a human body. It's very difficult to say what's going on. What you'll get is, okay, we can have some symptoms, but then by looking at those, can we make some predictions? So next, yes. Okay, so what we can do is, with these sensors, right, we can collect a lot of data, right? So in terms of historical or real-time data that we are collecting, again, in real time, use that to really see what is going on, in terms of when the unit is healthy and when the unit is, starts to degrade. Once we have this idea of what is going on, a very natural question to ask is, when will an event happen? And here with event, we mean like, something more critical, like something like a failure or a warning. And we would also like to have some idea of, what are the predictive uncertainty of when the failure will happen. And once we kind of have an idea of the future of what's going to happen, the next natural question is the prescriptive part. So can you click next, please? Yes, which action to take? Okay. Once again, so these are, let's say, some maintenance related actions, but you want to do it, again, you don't want the machine to fail, and you want to do, something in a prescriptive sense. So going next, what I want to talk about is different type of health related data that is often collected in these machines and how we can use them. So the very easy ones is something we call as event data, which are, what you also usually may have in maintenance logs, which just marks, when something happened at a certain point of time. And as you can imagine, event data is cheaper to collect, and it contains fairly rich information about the lifetime distribution of the machine. Can you click next? Yeah, okay. But some of the benefits of it, using, like event data, we can get some reliability estimates that can help us, ensure the service guarantees from the OEM side, or, perhaps effective monitoring, leading to reduced lead time or so. So that's one class of data. It's discrete in nature. The other class of data is where you are continuously monitoring what is going on with the equipment. So what you see here, for example, in the chart here are, let's say, multiple lead acid batteries. And we know that, lead acid batteries, they stop working once their internal resistance, goes really high or it saturates. So this is what you're seeing. Let's say, you're collecting data over time for multiple batteries, and maybe initially there is low risk of failure, but, as you go, ahead in time, there is high risk of failure. And so the good thing is you're collecting it very often, right? It provides real-time health information of what is going on. And it tells you all about the dependence, with respect to time. So you can see those trends, which are not really visible in the event data. But again, on the event data, you can collect a lot of type of things. For condition monitoring signals, you will need to have a lot of sensors. So, there are pros and cons on both sides. Both are really good in terms of, making those decisions, and so on. So the main goal or objective, with the data that we have collected, is that we want to predict critical events, that is failures. And then once we have some idea of what's going to happen, we would like to take proactive actions. Can you go next? Next. Okay, yep. So that's the objective. Okay, predicting critical events and take proactive actions. So what I want to give, talk about in the next few slides, give a glimpse of, how we can just do it from a data standpoint. So let's talk about the event data, failure event data. What we can very easily think of modeling is something called as rate of event occurrence. So let's denote that using lambda here. But if you look into the equation, it's fairly simple. It just says that, okay, what we are interested in modeling is that what is the probability of failure will happen given what has happened in the past in a very short amount of time. And very nicely, if you go next, we can, there are new models out there where we can actually model this failure probability in terms of environmental factors, what's going on around, who is the operator, what is the load, how long the machine is working, what type of machines are there, and so many things. So you can probably imagine that you have a model, that can incorporate different types of variety, variables, and so on, and give you that probability. And then once you have, once you have a model created, you can use that on a real-time setting. So what you see here is a historical database where you have that model with you, a new data, a new forklift, new machine, whatever is working in real time, you're collecting data. You can quickly update those model parameters in real time. And that can give us, again, in a real-time sense and a dynamic sense, what is the chance or probability of failing over time. So of course, over the time, we know the product or any machine will fail, but it gives us a very nice idea of how the probabilities will evolve going ahead of time. So yeah, if we take an average, we can always compute what is the expected time of failure. Can you go next? Okay, yep, that's the expected time to failure. Right. So that was, like an idea with the event data. Oftentimes, if you have sensors, you can have single sensor. Let's say, again, you're just probably measuring multiple here, like lead acid battery resistance, or you can have multiple sensors. Like, can you go next? On the right side, yes. So maybe you are, measuring the temperature of your machine. Maybe you are measuring, vibration levels on your machine and so on. And the real question is that we do see, that all of these machines are degrading perhaps over time, or gives us a signature and an idea that they are degrading over time. But, like, how do we know that how bad the machine health or how good the machine health is? So what we kind of, we can think of is that there is something hidden, like going on from state 1 through all the way to state K. And, state 1 is a good state, state K is a failure state. So what we want to model is how as the machine operates, how does it transition with respect to its own health states, and so on. And so once we create, with the data that we have, we can come up with these kind of models. Can we go next? Okay, we can just go to the next slide. And so once we have that model and we have this idea that, okay, as the unit operates, as time goes by, it degrades. But now that we have a model, we can, make a prediction of what's going to happen in the future using continuous signals. So what you see here is a plot of, predicting the remaining useful life, which is basically time to next failure, as the unit operates in a very dynamic sense. And so we kind of have some models to show that, these are far better in predicting when the failure will happen. And once we have predictions, the next idea is, how do we take decisions? So without going into the details of it, but we can come up with some decision processes, stochastic decision process specifically. And what it can tell us is, like in a real-time sense, at which time point, let's say you should do a PM, which is a preventive maintenance. So you keep on operating over time, and it will try to juggle that, what is the risk of failure every time point, and what is the risk of probably, or maybe probably benefits of doing a preventive maintenance. And it can give you those real-time, decisions, or at least empower you to make those real-time decisions. So on that note, I will also conclude this part and, this part of the talk, or probably the whole of the talk. So what I will conclude with is, yes, the era of digital revolution is underway, and from manufacturing or production point of view, this is the nice flow from data acquisition to data processing all the way to decision making. There's a lot of data that is being created, and so many opportunities that exist just to improve this whole manufacturing industry 4.0 and everything that is within this realm. And what I will talk about, I'd like to talk about next in the next slide is something is about the current project, that Dr. Kim, Dr. Lee, and myself, we are working or collaborating together, which is titled as Bridging Gap Between Legacy and Cutting Edge. So our kind of target, industry or companies are like small and medium enterprises, or SMEs. And so it is a fairly, like a real problem that, acquiring like smart systems or, very fancy cutting edge systems, they are expensive. So there is, of course, a way of, like doing a digital retrofitting. So where we have the existing machines, existing manufacturing processes, and we can employ sensors, right? So that we start collecting data. But there can also be, like leading edge machines that are working. So what it results into is something we call as mixed generational fleet. So where you have, let's say, some classical machines, legacy machines, and some cutting edge machines that are working together. And what we would like, what we are trying to propose here is because of just, two different, let's say, generations of machines trying to do the same thing, but how can we leverage the commonality or, make them learn from each other so that we can overcome this heterogeneity in terms of data that is being collected. So we would like to leverage, like enable transfer knowledge to enhance process control, prediction, and maintenance. And I'm probably looking at Minhee if I missed anything to say here. Okay, we're good. Okay, on that note, any questions? And just to highlight that we are currently looking for collaborators, for our research projects across many themes, not just limited to like, additive manufacturing, biomanufacturing, industry 4.0, industrial IoT, data analytics, perhaps beyond that too. Thank you so much.
Hey, thank you, team. That was really, really good. So let's open it up to questions. As you heard, if there's any industry folks online, they're definitely looking for some companies to meet. I mentioned before the webinar started, I'm going to try to connect them with a couple of people, as well as I mentioned too that Dr. Barger, as part of one of the NSF grants that she manages, actually created did a lot of the work that they showed us today using an Arduino type product. So we're going to get back with them, get back with this team on that later, and they're thinking about putting in a grant to do just that. So more to come on those. So let's open it up to questions then. Are there any questions from the team? Does anybody out there have any experience sort of doing what they discussed or has done any research on their own? I know this group isn't usually shy.
So we're looking at starting to upgrade some of our capabilities from an IoT and an active data management system. I mean, we have a lot of experience on actually doing predictive maintenance type stuff from data acquisition for our engines that we manufacture for our final end product, but not actually for our internal manufacturing process, right? Some of the challenges to getting started, though, like you said, the first couple of slides resonated, the cost barriers coming down, but there's not holistic type systems or resources like in the design engineering side when we're designing the engines to do the implementation. And you've got to implement them with dozens of other systems that you may have, from quality control, ERP, MES type, and it's right now it's like bolting on another. You almost need a programmer slash data scientist to help set it up. So that cost barrier to entry from the equipment has now went away, because now I need to hire 2 or 3 more IT type folks or data analytics folks. And the pushback is, well, now I've got a document management system, ERP, SAP type system, and then this one lives somewhere by itself. Maybe you have another maintenance system and they're not integrated. So it's just, you get frustrated on how can I actually do it. This is the challenges we're facing.
Lonnie, would you mind explaining a little bit about your company, what you do, or the project you're talking about?
My company, Power Systems Manufacturer, we grew up as a design, engineering, and product company for gas turbines, industrial gas turbines primarily. So we make upgrades, repairs, field service, predictive maintenance modeling for engines out in the field. Over the past decade, we've started growing our internal manufacturing capability. So now we have quite a sizable internal manufacturing capability, where still most of it, but predominantly, was managed by an external supply chain supplier base.
Okay, thank you. I just want to get a little perspective. So I guess maybe we'll go back to the research team here. I don't know if you guys have a response to his question.
Sure. So that's like, I think that's everyone's problem these days. Like we saw from news that, oh, AI is doing this, AI is doing that, like it will replace everything and like enable everything. But the problem here, especially in manufacturing, is that the transformation from the existing systems to whatever AI enabled systems is very like the gap is really large. Like all, and sometimes, okay, I want to do it like step by step. I want to transform this aspects, and based on it, I want to transform it here, and I want to step by steps. But as you just explained, sometimes it's not possible. We have to do like one chunk, which requires a huge initial investment. Like we have to hire new people, like we have to overhaul the current systems and so on. So it's actually a big problem, and there's like one golden solution to it, unfortunately, because even the research team, like on the front end, also like suggest like many ideas to, okay, how to close that gap, like how to, maybe we cannot close the gap entirely, but maybe at least we can have these intermediate steps going from like one legacy to like one cutting edge. So that's actually a really good question, like important challenges that everyone is tackling these days. Akash, Jaesung, if you want to add anything, feel free to chime in.
I do not have anything, like significantly add here, but it is true, like, there is no existing, let's say, a kind of an MRP or ERP, SAP provider, which, gives you that whole framework. As you can imagine, it has, both the hardware and the software aspect coming together, plus the communications. Some of the bigger, I know, like Microsoft Azure or AWS can offer some of the services when it comes to managing the data, collecting the data in real time. But yeah, to my knowledge, to the best of my knowledge, I do not know if there is a very nice, cohesive solution out there that we can just readily implement. I think we all are probably just working, towards it. Yeah, as we make, take those baby steps.
And
Yeah,
another,
sure, but that's the barrier to entry to actual industry, right? It's still at a very high academic level, especially when we talk manufacturing. Most manufacturers don't have that skill set or knowledge, especially depends on your scale size, right? So yes, General Motors or Apple or someone, like that, but a lot of manufacturing is small niche type companies. I would even consider us probably medium size, and we're at 40 to 60 million a year. We don't have those type capabilities, of course your large blue chips may, but that's even most of our suppliers that manage our supply chain are probably on the size of what we are, that 30, 40, 50 million a year total revenue. They don't have 5 million to go invest in people and personnel to study AI implementation of workshop management.
and another obstacle I noticed from educator and / researcher viewpoint is that it is expensive, as you explained, like the initial cost is really expensive. And despite of this initial cost, it is really uncertain how much it will how much it will pay back. Like, okay, to see if this will work or not, we have to see like small success, but it is really hard to even see the small success in small platforms. So that's another like challenge I notice. And as you mentioned, like when I also work with students are really interested in research, and students are interested in data analytics and manufacturing. Not only my students at UF, but also Dr. Deep and Dr. Lee know many students who are interested in, but it's just from students' viewpoint, there are not many venues that students can explore. They're interested in manufacturing, they're interested in data analytics in manufacturing, but most of those data analytics opportunities that they can seek is like those software companies where they have to grow software like coding, programming experiences where they're not their like primary interest. Yeah, so I think there are students and there are job seekers who are interested in those things, and there, as you as the questions, there are people who are seek those talents, but I think there's still a gap between like connecting these two group of people. Yeah.
Yeah, and real quick, Lonnie, if you want to connect with me offline, there is I know of one company, as I'm sure there's many that help implement this. So if you would like, to just reach out and see what they have to say. Also, I just mentioned it to the research team before before the webinar started, but there is a federal institute called SESME, which is a Smart Manufacturing Institute, and that's what their whole purpose is to help small mid-sized companies, get into automation. Florida Makes, which is who FLATE is under, has recently partnered with them. So there's a lot more information to come. But certainly over the next year or so, we'll be partnering with SESME on a bunch of projects, and certainly we will let you know as that comes to fruition. But yeah, let me know if you want to connect with a company that can at least give you some advice, and maybe you can make a call from that point on if you want to move forward or not. But there is some help out there for sure. Let's see, we've got, oh, go ahead.
I was just gonna say, there's another question in the chat.
Yeah, thanks. Is that Jeremy? Yeah,
Yes.
Jeremy put in the chat. I don't know if everybody can see it. but it says Jerry from Columbus State Community College. I'm curious what amount of data cleansing tends to be necessary within manufacturing currently to be able to utilize AI on all the sensor data streaming into platforms like Redis, Snowflake, etc.
So it depends, but based on my experiences, it's a lot. So usually when I like work on those industry projects with my students or other people, once we done data cleaning, which says, okay, like we are at least half or more than half done. So when we talk about AI, data analytics, we all see this like futuristic algorithms, like visualizations, some of the visualization we showed you earlier in our webinar, but the time we have to spend is like half and more than half is about like data cleaning. It's a really like dirty manual things that still have to happen in manufacturing data. And I think that's one of the reasons why, although the amount of data collected from manufacturing is huge, all the fancy applications we see from AI usage is not from manufacturing. It's from like those human like ChatGPT kind of things, because the data we collect from manufacturing still requires a large amount of like labor-intensive data cleaning.
What I want to point out is, we all know the data cleansing is very important and it will take a huge portion of the data analysis. But then ultimately what we want to do is we want to build a pipeline of the data cleansing. So we have all the data that has a lot of like noises or the environment, something special to it. But once you build a pipeline of the data cleansing, then the process will just cleanse the data, then it's ready to go. Then you can use it for the data analytics to achieve the whatever goal you have.
Very helpful. Thanks.
Thank you.
Do we have any other questions? Was there any follow-up, Jeremy?
Only that confirmed my suspicions that that's still the #1 problem in industry and everywhere is the data analytics problem of just getting the right data to start with.
Yeah. All right, so we've got about 2 minutes. We probably have time for one more question if anybody has one. Okay, well, I want to thank our research team, Dr. Kim, Dr. Deep, and Dr. Lee. Really appreciate your time. This is a fascinating look at what's happening not just now, but certainly in the near future. As I mentioned, if you're a company and you want to learn more about how to automate your facilities, certainly these researchers here are looking for some companies to work with. But we can also help you connect maybe with some folks that can help you make that transition. And as I mentioned, as we partner more and more with SESME, we'll reach out to the companies that are part of the network in Florida and provide that kind of training in the near future. So if there's nothing else, everybody have a great day. Thanks again for this great presentation, and we'll see you all soon.
Thank you so much.
Thank you, everyone.
Thank you, everyone.